All right, so we're in section 2.1. Our objectives are to define what a limit is, find one- and two-sided limits, and apply what we call the sandwich or squeeze theorem. So in order to be able to do that, we're going to talk about a little bit of vocabulary. And some of that vocabulary is average and instantaneous speed. So the average speed during a time interval is found by dividing the distance covered by elapsed time. So you could find your average speed when you're driving. You can have your average speed when you're walking. So if you think about driving, when you're on a turnpike, you enter and exit a toll plaza. If you enter and exit the toll plaza and you exit it at a speed or a time that is much quicker than the speed limit, they can actually send you a ticket because they can find out your average speed and determine that your speed is averaging over the speed limit the entire time. So like, let's say you're on the Ohio Turnpike, you're going to Cedar Point, the speed limit's 70, and you get there and you drive, in 2 hours, you go 180 miles. They know that you were driving more than 70 miles per hour consistently, and they can send you a ticket. So it's total distance, which in that case would have been 180 miles in 2 hours. So that meant you were averaging 90 miles per hour. That's your average speed. Instantaneous speed is a lot like driving a car also, but it's the speed your speedometer is showing at that exact moment. So it's the speed at that exact moment. Instantaneous speed is not constant. Unless we're in cruise control, and even in cruise control, if you're on hills, you're not going a consistent speed. Our velocity is constantly changing, maybe by 1 or 2 miles per hour, but it's the instantaneous or the speed at that exact instant. You guys in physics, that should probably make a lot of sense. So a rock breaks loose from the top of a tall cliff. What is its average speed during the first 2 seconds of fall? So we need to know 2 things. We need to know what is its speed at its initial time. And we need to know what is the speed at 2 seconds. So we know that a solid, dense object dropped from rest freely near the surface of the earth falls at 16 t² feet per second. So 0 would be 0. At 2, it would be 16 times 2 squared. Well, 2 squared is 4. 4 times 16. 64. So then its average speed is 64 minus 0. So speed at 2 seconds minus speed at the beginning, all over total time, which is 2 seconds, or 32 feet per second. Find the speed of the rock at the instant t equals 2 seconds. So we actually already did that, right? We found the speed of the rock at 2 seconds. The speed of the rock at 2 seconds was y of 2, or 64 feet per second. Okay, in the preceding example, most limits of interest in the real world can be viewed as numerical values. We can view a limit in many, many ways. A lot of the limits we're going to start with today are going to be similar to the worksheet you did yesterday. We're going to simplify through algebra to get down to a value. Limits give us a way of finding an output that we cannot find. So limits find us an output that we can't normally find. So on that worksheet where you had holes, those would be outputs that you can't find, right? You cannot find the value of that hole. Well, by using a limit, we're going to be able to find the value of that hole, or at least what was infinitely close to that hole. So a limit allows us to find a value infinitely close to the hole or denominator that we could not normally find. The limit of a function is the way of describing how the outputs of a function behave as the inputs approach a particular value. They allow us to find the outputs of a function and its behavior as we get close to a particular value. The definition of the limit is the limit as x, which is our input, approaches c. So as x is getting close to the particular value c, what is f of x doing? That value is L, known as our limit. So the limit as x approaches c of f of x equals L. This notation means the values of f of x of the function f approaching or equaling L as the values of x approaches. It does not mean that f of c equals L. Let me specify that. This does not mean f of c equals L. This does not guarantee f of c equals L. So like this does like that, it can be, but it doesn't have to be. So that's like really hard to describe, but f of c can equal L, but it doesn't have to equal L. So graphic examples of limits. So you might have a curve that looks like a quadratic. We're going to examine that quadratic at a particular point we'll call A. What a limit as x approaches A does, it says, okay, what's happening at this graph as we're getting close to A from this direction and from that direction? So what's happening at the graph? Well, it's getting close to some number L. So the limit as x approaches A of f of x equals L. Where a limit is different than a normal graph is that you could also have a hole on our graph. So here's my C. So we could say the limit as x approaches c. So you're looking at the graph, you're saying, okay, what's happening as I get close to c? Even though f of c does not exist, the limit as x approaches c of f of x, which is the red graph, equals that whole, which we're calling that point L. Okay, so we can look at limits by looking at their graphs. So here we have three equations. We have f of x, g of x, and h of x. So in example A, it says find the limit as x approaches 2. Should be as x approaches 1, sorry. They should all be 1s. I hit the wrong keyboard spot. Sorry, kids. So find the limit as x approaches 1 for f of x. So what we're going to do is we go to 1 on my graph, and I know down here that if I tried to find f of 1, right? So here's f of x. It's x squared minus 1 over x minus 1. If I told you to find f of 1, you'd get 1 squared minus 1 over 1 minus 1. So you get 0 over 0. Can you divide by 0? No. So that's why there is a hole right here. And if you think back to yesterday's lesson, where I had you factor, if you factored f of x, the top is a difference of squares. So those cancel. They gave you that hole, right? You could see where the hole came from. We all agree? And then you see that this is a line shifted up 1, hence the graph we drew with the hole at 1 from the denominator. So because you have a hole at x equals 1, your graph becomes x plus 1 when you graph it. We obviously don't have a value for 1, but what we can do is say, okay, what's happening on that graph as I get close to 1? So it looks like it's getting closer and closer to what number? What number is it getting close to? 2. So the limit as x approaches 1 of f of x equals 2. The limit as x approaches 1 of f of x equals 2. How about over here? G of 1 based on this piecewise is equal to what number? Based on that piecewise, where do you plug in the number 1? To the top or the bottom? Bottom. So G of 1 equals 1. The limit as x approaches 1, however, is equal to, what's this getting close to on the graph as we get close to 1? Yes. So the limit is equal to 2. However, the function was equal to the number 1. So that's what I was saying in the previous example. The function value does not have to equal the limit. The function value does not have to equal the limit. Function value does what? Yeah, it does not have to. Can it? Yes. So that's the last example, right? So h of 1 would be equal to what? H of x is equal to x plus 1. So h of 1 is equal to 2. As I get close over here, what's my limit approaching? 2. So in example C, the function value and the limit are the same. What's the difference between example A and B versus example C? There's a word that we could use to describe C that you can't use to describe A and B. Yes, excellent. C is continuous, where A and B are not. So continuous functions have limits that equal their function value. That's coming in section 3. Two really important properties of limits are the limit as x approaches c for a constant k is equal to k. So k in this case is a constant. What's it mean if you're a constant? What does that mean? There is no what? If something's a constant, it has no what? Yeah, no variable, no variation, there's no change. So k means there's no variable in that problem. Numerically, this would be like saying the limit as x approaches c of 5. Well, if y is equal to 5 always, then the limit at any point is equal to 5. If it is a linear function with no transformation, so the parent linear function, x, then it's always equal to c. So that would look like the limit as x approaches 2 of x. Well, no matter what value I plug in, it's going to be what my limit's approaching. So the limit as x approaches 2 of x would equal 2. The limit as x approaches negative 100 would equal negative 100, etc., etc. If your limit or your function is x, then it will always equal whatever x is approaching. If x is approaching c for a limit, then one of our techniques is direct substitution. So in order to find the limit value here, because this is a polynomial, what do we know about a polynomial? Polynomials are continuous, right? So a polynomial is kind of like x. If you have a polynomial, then your limit value will always equal that polynomial substituted in. So the limit as x approaches c of x cubed plus 4x squared minus 3 for some number c will equal c cubed plus 4c squared minus 3. If instead of a generic constant c, you could say the limit as x approaches 1, I'll keep it nice and easy, of x cubed plus 4x squared minus 3 would become 1 cubed plus 4 times 1 minus 3. So 1 cubed is 1, 1 plus 4 is 5, 5 minus 3 is 2. So C is just acting like a constant. So it could be any number in the universe, and then it just plugs in. Example B, the limit as x approaches C. So once again, you plug it in. You'd get c to the 4th plus c squared minus 1 all over c squared plus 5. I don't have to worry about that denominator because c squared plus 5 is a quadratic shifted up 5 units. If a quadratic is shifted up 5 units, is it ever going to cross the x-axis? No, because the denominator is always going to equal a non-real. So I don't have to worry about the domain of example B because the denominator is never going to equal 0. Okay, example 1, find the limit using the properties of limits. So once again, I have x squared and 2 minus x. So even if I distributed that, this is what type of function? X cubed is cubic, which is a grouping of polynomials, right? So it's a cubic function, which means it's a polynomial, which means it is continuous, which means we can plug in using substitution. Yeah, I just wanted you to see that it was cubic. So we have 9 times 2, which is 18 minus 27, or negative 9. Okay, and example B, once again, what do we have to be concerned about in our denominator? Yeah, so x cannot equal, since x plus 2 can't be 0, x does not equal negative 2. Are we looking for the limit at negative 2? No. So the limit value we're looking at is part of the continuous function. Therefore, we can plug in using substitution. That's a whole lot of 2's. Good? True. All right, so now I want you guys to try to work through that next one with me as opposed to falling asleep. So we have the limit as x approaches 0 of 1 plus sine x over cosine x. So we plug in This is why it was so important to know your unit circle. So the sign of 0 is 0. The cosine of 0 is 1 divided by 1 is 1. So the limit as x approaches 0 of 1 plus sine x over cosine x is 1. Bump, bump. What happens in this next example? You get 8 minus 1, which is 7 over 0. If you get a number over 0, the limit does not exist. If you get 0 over 0, the limit exists. If you get a number over 0, the limit does not exist. Are you guys laughing because of the scene that's from? What? I literally just watched it 2 weeks ago. No, the boys have no idea what I'm referencing at all, do they? No. I'll show the clip in a minute. Yes. The limit, no. The limit as x approaches pi over 2 would equal 0. But the cosine at 0 on the unit circle is 1. You're flip-flopping your values. So again, a number over 0 is the limit does not exist. 0 over 0 means you need to simplify. So 0 over 0 means you need to simplify. That's called the indeterminate form. So we're going to talk about that probably next. Okay, 3 more problems. You can do it. So now you guys have tables on your papers, right? Now we're going to get out those handy dandy calculators, but we're also going to do it algebraically. So I'm going to show you calculator and algebra. So we're going to do a little bit of both. So let's start with the algebra. If you were given this problem, you have the limit as x approaches 1 of x minus 1 over x squared minus 1. What happens when I plug in 1? Yep, go ahead. I get that 0 over 0. I drew an extra, there we go. So 0 over 0, I told you this is called the indeterminate form. So the indeterminate form tells me that I can simplify. Algebraically, what could I do to the denominator? The denominator is a difference of squares, which tells me I can do what? Yeah, I can factor it into that x plus 1, x minus 1. When I factor that, what happens? The x minus 1s. So you get the limit as x approaches 1 of 1 over x plus 1. Now, can I plug 1 into that? Yeah. So if you get 0 over 0, it's not a DNE. It is usually a hole on the graph, which means you have the value it's approaching. And that's what we're going to look at. That's why we're going to take out the graphing calculators for a minute here and look at the graphs. So what I want you to do is take out your graphing calculator. You're going to go to y equals, and we're going to plug this in. Bear with me for 1 second. Let's try another one. Okay, so first, I want you to look at the algebra. So go ahead and plug in 0. What happens when you plug in 0? What do you get when you plug in 0? Yep, we get 0 over 0, which is the indeterminate. Algebraically, in order to simplify this, you have to use what we call the complex conjugate. So that means I have to multiply by the, so this is like a difference of squares. The complex conjugate would be t squared plus 9, same beginning. You change the sign, so it becomes plus 3. So the complex conjugate is like a difference of squares because your ideal is to cancel the middle terms. And then if you multiply your top by it, you have to also multiply your bottom. They don't cancel though. What we do is FOIL. So square root times square root go away. So you get t squared plus 9. The middle terms in a difference of square always cancel. So you get negative 3 square roots of t squared plus 9, positive square root of t squared plus 9. So they cancel. Negative 3 times 3 gives negative 9. All over t squared times all of this. Positive 9 and negative 9 cancel. So then you get t squared over t squared times all of that. So they cancel. So you're left with the limit as t approaches 0 of 1 over square root t squared plus 9 plus 3. Now you can plug in 0 and you get 1 over the square root of 9 plus 3. Or 1 over 1/6. Using our table, we're going to do the same thing we just did previously, but now my middle term is 0. So I still follow that same rule. You add 0.001, 0.01, and 0.1, and you subtract 0.001, 0.01, and 0.1. So instead of being 0.9, now it's 0 minus 0.1, which is negative 0.1, 0 minus 0.01, and 0 minus 0.001. So you go to your table, you change your y equals to now be this equation. So you have second square root x squared plus 9 minus 3 over x squared. Change your table. And in your table, you should get 0.166, 0.166, 0.166, error. And what do we know about the value of 1/6? 1/6 is 0.1666666 repeating. So you can see how the table and the limit give you the same value. Are we okay with getting that on the graphing calculator? Because usually I can put my graphing calculator up, but like I can't put it up right now. If we're not, I'll try to make a short video just doing one of these problems on a graphing calculator so you can watch me doing all the key presses. Okay. Might even be able to do that for the next one. We'll see how stealthy I am. Correct. Always the original. So last one, you get 3 to the 0 minus 10 to the 0 over 0. Anything to the 0 is 1. So you get 1 minus 1, which gives 0 over 0. Algebraically, do you guys know how to simplify that? Probably not, right? Yeah. So exactly, you would have to like ln everything, and they would never make you simplify. This would be an all graphing calculator question. This one, to simplify algebraically, because you have 2 ln's, is going to become very, very kind of not so nice. If the bases were the same, it would be a little different, but they're not. Honestly, before I ln'd, you could even rewrite them both as logs and then use your logs to write them as a single logarithm using the idea of subtraction. Let's do it on our graphing calculators then to see what the value of the limit is. I wonder if I go, doesn't shadow on you. So you would go to y equals, clear out anything you had in there. This is where I was telling you about the second alpha. So you can hit second alpha. Oops, sorry, mine's all goofed up. So you hit alpha and y equals. That gives you the n divides d, and that allows you to type in an actual fraction bar. So we do 3 to the x minus 10 to the x all over x. Hit second table. And we know our middle number needs to be 0. So my x values here actually stay the same. So you'd have negative 0.1, negative 0.01, negative 0.001, 0, 0.01, 0.01, and 0.1. And then your table would get filled in with the Y1s. So what does it look like this is approaching? Negative 0.12? Negative 0.12. Everybody okay with that table? So your homework is in that book, and it's on page 66. You're doing 1 to 30 all. I can promise some of them are just some algebra. And then tomorrow, if you haven't already been alerted, there is Khan Academy. So,